Hello, everyone, and good afternoon. Welcome to the Azure DataFest, our event, and this is the third session. I'm as usual, some trouble so for me to change slides, but I'll do that shortly to show you the calendar of session. Okay, here it is, and yeah, as you may remember, for those of you that have been with us since the beginning of this event, this is the third session. We are continuing our exploration of Azure Data Explorer, or Kusto, as it is also known as. And last time we did an introduction to what Azure Data Explorer does, and we are building on that foundation today to investigate and deep dive more into what are the features and capabilities that Azure Data Explorer exposes in order to build highly concurrent and performant applications. Okay, we have also extended our calendar of events beyond October in November to also talk about not only all the services that Azure provides for you to perform mainly big data analytics and analytics on real-time streaming data and machine learning, but also to explain and deep dive in what are the infrastructural services that can be put in place to productionize your deployments, secure them. And so we have introduced additional sessions that target exactly these topics. And you could see actually we will run these events all the way to the 2nd of December, when we will explain how I will introduce a little bit more at depth the topic of security, how to secure your infrastructure and visualizing threats. So data services, yes, but also deploy and run them in a production environment in a secure way. Moving to the next slide. It's a bit of lag, but surely, yeah, let me introduce a few things just before we get started. So as you know, at Microsoft, we see sustainability and humanity's response to climate change as one of the greatest challenges of our lifetime. And we believe it is not too late to plan for a cleaner and greener future. And therefore, as part of our commitment to sustainability, Microsoft Singapore will be planting a tree for every person attending this event. Moving on to the next slide, a few housekeeping rules. So the session is being recorded for those of you that want to replay it afterwards. You can ask a question throughout the sessions. I will be your moderator, and eventually I will liaise with our presenter today, whom I will introduce shortly, to expose your questions, because you will be on mute, and but you should see a Q&A panel where you can enter your questions, and I will be reading them and responding to them. At the end of it, of this session, we will also reserve about 10 minutes for a Q&A sessions, so we can elaborate on some key questions or questions that require a lengthy explanation at the end of the session. All right, so without further ado, let me introduce you Avner Aroni, Principal Program Manager of Azure Data Explorer, which today will help us deep dive in some of the key capabilities of the Data Explorer service. Thank you, Avner. Thank you for being with us today.
Thank you, Andrea. Hi, everyone. Nice to be here. So I'm going to give the talk about building high concurrency applications on Azure Data Explorer. So I'm going to talk in this talk. I'm just going to start with introducing the use case, then talk about the applicable features that Azure Data Explorer Kusto provides to fulfill this use case and scenario. And then I'm going to touch a bit about the UI stack and how to build the user interface and what are the different user interfaces available for such an application. Okay, so let's start with the use case. So we see quite often in Azure Data Explorer, which is a big data platform that supports, it can ingest terabytes and petabytes of data and present it to the users in a very fast manner, very performant. We see a lot of our users are building large-scale dashboards and alert solutions. And the data is flowing all the time into the system, and the users, we want to build for them a dashboard. Many users are touching those dashboards. There are many dashboards. There is alerts running all the time on top of the data. And the usual telemetry, monitoring, and diagnostic and stuff scenario. The spec that I'm going to show you and the example that I'm going to use in order to exemplify the scenario is from an actual use case that we were looking a few months ago. And in this spec, we wanted to build a solution that will accommodate more than 1,000 users that are using data that is collected from telegraph agents, collecting around 34 million metrics per hour, all in 10 seconds of granularity, keeping them for 15 months and building more than 2,000 dashboards and including alerts that runs all the time, tries to detect anomaly and things like that. The acceptance testing that we've done for such application is to have 100 concurrent users that are hitting those dashboards. We created 7 different dashboards with 3 different time spans and auto refreshes and things like that. Each dashboard had at least 6 tiles with multiple time series and week-over-week calculations. Everything has to load very fast within 5 seconds to get the full dashboard to load, and everything has to be fresh. The data should have been less than 2 minutes since it was created. So as you can see, this is a super demanding system to build, and for that we invested a lot in creating features and perfecting different features that we already had. So let's talk about the different features and capabilities that ADX has. The first feature is Materialized Views. Then we have the leader and follower pattern. I'm going to talk about data partitioning policy, query consistency, and query cache results. So I'm going to drill next on each of those features and tell you more about them and how they can help building such a solution that accommodates this traffic. Let's start with a materialized views, that has 3 main use cases. One is the downsampling, is the ability to have a view that always calculates in the background and calculates downsampling of the data, meaning aggregates of the data in different buckets than the one that you received. For example, if you're receiving telemetry every 10 seconds, but you want to keep the data in a granularity of 1 day, you can summarize it by this bucket of 1 day, and then when everybody queries the data, they don't have to go through the full data set, they can just look at the aggregates. The second case is saying the last entity by the update time. This is a case where there is a sensor, the sensor sends the state of that sensor all the time, and you're only interested to see the last view of this sensor. What is the current temperature? How far the bus is for me? Things like that. And so in Kusto, we have a very nice operator called, in the summarize operator, we have a nice function, I should say, called argmax. Argmax allows you to say, based on this column, get me the last row that has this, that has all the different values in this row by any dimension. It can be by ID, by tenant, by any dimension, by sensor, or something like that. The third scenario is the deduplication. So unfortunately, from time to time, we see systems that has duplications in them. And then our users come to us and say, we want to first deduplicate the data. We really care about not having duplicates. And then we want to do other calculations. For that, you can run a summarize take any by the different by the different keys that you're interested in. And this calculation is very heavy if you do that during the query itself, so you can do that in a materialized view. So those are the three scenarios. And when you create materialized view, it does cost you in computation in the background, but it gives you a great performance improvement. And it's always fresh. You always get the data fresh. It's always the whole data, aggregated, deduplicated, last value, all the scenarios that you want, and you get the right data, always fresh, always up to date. It allows you to reduce the COGS, the cost of the cluster, and it's a fully managed solution. Transactional guarantee, meaning that you don't need to do any heavy lifting, you just define the view, and Azure Data Explorer Kusto does the work for you in the background. So before we move to the next section, I'm going to show a little demo. And let me just find the right slide. I think it is this one. Okay. And here, I took, this is a demo that runs, by the way, on our production cluster. And I took a table that is essentially like a sensor table. Okay, so every few minutes or something, it surveys all the different clusters that Kusto has, and it sends a little record that says what is the cluster name, when it was last updated, then it tells us what is the SKU that it runs, and what is the machine count, okay, of that cluster. Let's run this query, see the result. This is what we have in this table. In this case, I just filtered for my own cluster, and I'm getting 1,000 reads on this cluster that tells me that in all these times, my cluster had a specific machine and a specific machine count. Okay. Now, if I want to run that and to see just my latest view of the cluster, I can say argmax by the timestamp. This will give me the last record that I had for this cluster, for this specific cluster, and I can see that state of the cluster. Okay, so now let's look at, we have a nice view here that allows me to focus on the query statistic. Let's look at the performance of this thing. So it will run that, and I can see that it took half a second to run, very fast, but it took 13 seconds of CPU. So the cluster spent 13 seconds of CPU time to calculate it. Now let's look at the materialized view that I created for this. This materialized view is essentially the same query. It just says dim clusters, which is the original table, summarize argmax, last updated, meaning give me the last record, by the source, by the cluster. And so for each cluster, it will calculate the latest record. Now let's run the same query on the materialized view, and this time also we'll focus just on the statistics of that, and let's see how long it takes. So it took 3 times faster, but from performance of the CPU, it took around 100 times less CPU, right? You see that it improved the CPU consumption from 13 seconds, it reduced it to 156 milliseconds. Okay, so that's the type of performance improvement that you should expect. And this is a super, super powerful feature. Okay, let's continue this deck and talk about the next feature. So this is the leader and the follower. In Azure Data Explorer, when you send the data, when you ingest the data, it goes to a cluster. You can ingest the data to this cluster, you can read it. Essentially, the cluster is a read-write cluster. But in many cases, you want to have a cluster that only serves the reads. Why? Because maybe I should go through the next slide, I should go through the reasons. But essentially, what the follower and leader pattern allows you is to create many read-only clusters that we call followers that follows the read-write cluster. And you can follow a database, you can follow a table, you can follow only specific tables in any other cluster. Okay. So when do you use it? You use it to share the data between different organizations and teams. Let's say that one organization is responsible of getting the data, ingesting it, and maybe has its own workload. And then some other team, the machine learning team, want to run some machine learning algorithms on that. Obviously, if they run it on the main cluster, on the read-write cluster, it will interfere with their work. It will consume CPU. It will reduce the performance of that cluster. So they can simply create a follower cluster, and now they don't impact any of the resources of the other clusters. And you can create as many departments, many teams can use the same data without interfering with each other. And the other thing that it allows you also to split the cost between the different teams, because if one team is using that and you want to ensure that they pay for that, they can come with their own cluster essentially and pay for that cluster, and then the other team doesn't have to run the cost of that workload. And then the other reason that was super important for our use case is to separate the ingestion from queries. So in our use case, if you want to have a really performant high concurrency solution that runs dashboards, you don't want the ingestion workload to interfere with that. You don't want to have a spike in ingestion and all the dashboard works slower. So what we did in our solution was to create a leader cluster that does the ingestion, have a follower cluster that does the serving of the dashboards, and then they didn't interfere with each other, and then we can get predictable performance on both clusters. And the features that it provides is, like I said, you can do that on a table level sharing. You can change the permissions, so you can have one set of permissions on the leader cluster and one set of permissions on the follower cluster. A cluster can be both a leader and the follower, so you can have the cluster has one database that does the read-write and another database that is following yet another cluster. So like I said, a single database can be followed by many followers, and a cluster can follow databases from many other clusters. So it's a super flexible and useful technology. It's really the really incredible technology. Okay, one thing to note when we talk about that is that the follower and the leader has to be in the same region. The reason is because they're both looking at the same storage accounts for the data. So they don't share the same compute, but they share the same storage. And if you try to have a cluster on a different storage account from a different region, the performance will suffer from that. As a result, we disable this ability, and you can only have the leader and the follower in the same region. The other thing to note is that there is a data latency because the leader is always up to date. It's ingesting the data. The follower is synchronizing with the storage account, so it takes it a bit of time to synchronize, up to a few minutes. And so because of that, you should expect a latency on the follower. There is ways to get around those latency. One of the things that we did in our implementation is to have views, essentially functions, that union between the follower and the leader, and takes only the latest data, the last, sorry, 10 minutes from the leader, and then the rest from the follower. That's how we circumvented this limitation of the follower. But some other people don't mind about having a couple of minutes to be behind the leader. Maybe they're doing, like I said, machine learning. Maybe they're doing some other scenarios. But in any way, you can override it or overcome that essentially by creating a union between the leader and the follower. Another good thing to note here, or important thing to note, is that there is two settings for the prefetching of the extents. The follower can answer the queries and show the data that arrived even before it caches the data. As soon as it sees that there is a new metadata for the leader, it sees the new extents, it allows you to run queries on them, but the data might not still be on those nodes cached. That obviously leads to cache misses that might lead into performance hiccups or performance degradation. You can set these prefetch extend settings to true, means that until the whole data is cached on the follower, it will not allow you to query that data. And that allows you to have a very predictable and a very predictable and very good performance. So for the scenarios that we used, we set it to true. So we always wanted it to be fully cached and fully warmed up before the user could query that. Okay. Now let's talk a bit about data partitioning. Data partitioning is also a super important capability in databases. In Kusto, we're doing that extremely simple for you. So you essentially need to define it once as a policy, and then you get the benefits of partitioning. So now when the query runs, it will know how to find the right partition. The partitioning policy on Kusto is really advanced. You don't see that in the model. So in other databases, the partitioning concept is exposed to the user or to the developer. They need to tell the engine, they need to tell them if they're using a specific partition, they need to filter by partitions, they need to do some work in order to use it. In Kusto, it's all hidden for you. You don't need to worry about it. Once you set it up, it's completely hidden. The system would know how to take advantage of the partitions, but from the user perspective, it's all transparent. It's really nice and simple model. So the partitioning policy is essentially, you can say two things about it. You can choose one string column and one datetime column. For those columns, the system will ingest the data, and then in the background, it will repartition the extents, our data shards, it will repartition them by those columns values based on the definition of the partitioning. And then all the queries that will run on top of that will take advantage of this partitioning. One of the main advantages is what we call the pre-filter. So when we run a query, we're looking at the metadata first to find the values that you're filtering on. For example, if you have 34 million different metrics, and every time you just query for one single metric, let's say that you have 100 partitions, 128 partitions, instead of searching for that specific metric across all the different extents, it will search it only on one out of 128 extents, but it will do that ahead of time. It will know exactly what extents has this information, and it will pre-filter the different extents by the partition values. The other advantage that it has, it will allow you to move less data between the nodes of the cluster. So that means that it will perform the calculation in a more local manner, and obviously it will improve the performance. When do you use it? First of all, you use it, first of all, I should say it costs. This is the warning at the end. It costs CPU for the cluster because the cluster is constantly partitioning in the background the new data as it arrives, and this is a demanding workload essentially. It takes every partition, it takes every extent of every extent that arrives and breaks it into 128 or the number of partitions that you specified. The default is 128. It will break it into those extents, and then it will merge them, and it will do other background operations on them. So it's obviously it costs CPU. So you want to use it when you're really going to benefit from it, when the query performance is going to be so so greatly enhanced that it's worthwhile spending the CPU in the background to set it up. So the first thing that you do is that you need to ensure that that majority of the queries are filtering on the partitioned column. In the example that I gave you, if you have 34 million metrics and every tile in the dashboard is filtering for a specific metric or few metrics, and then obviously partitioning on the metric value is going to make huge difference. In our experiments in that solution, it was at least 10 times faster, right, and 10 times less CPU. So you really want to do that when the partitioning column is used either in filtering or in aggregation. The second reason for using partitioning on datetime is when the data is coming out of order. Sometimes we see that that the data, because the client clock is skewed, and sometimes we get data in the future, sometimes we get data in the very fast past. It just corrupted data essentially. Or sometimes there is a lag in the data from other reasons, and you want to make sure that when you query, only query the ranges correctly. You don't have these values mixed with other values, because that essentially destroys the index of the time index, the time filter index. Then you can set the partitioning also on the datetime column, and that will ensure that all the extents will be homogeneous as it relates to their datetime column. Let's look at another demo. This time look at the demo for the partitioning. And here, this example, I'm looking at a data set that has 4 billion records. And I'm going to look for, I created a partitioning. I have a logs table that is not partitioned, and then I have a logs partition table that I apply the partitioning on the source column. Let's for a second look at the partitioning policy before we start the demo, and look and see what it has. So it has a partition on 2 columns. One is the source column, where you see that I'm using here the filter, and it's a string column. It's using the hash partitioning. It has 128 partitions. And then the second partition is on the timestamp column. I'm not using this in the query, but it's just partitioning that based on a specific day. So for each day, there will be its own partitioning. And I'm setting that the effective datetime is in the past. So I can also partition all the data that I had so far. So I did the partitioning in this logs partition table. I have this table that is doing, that is not partitioned. Let's click on the view and focus on the statistic immediately. So we don't need to worry about this. And here we see that the query time and the total CPU time. And now let's click here and focus on the statistic.
Avner, sorry to interrupt you. I just received some feedback that maybe the font may be appearing a little bit small on screen. I don't know whether you have the possibility to zoom. Otherwise, it's still readable.
Yeah,
just that it is small.
Definitely, I can zoom. Here is a.
Thank you.
Yes, this is Kusto Explorer. Everything is easy in it. Great. So you can see here that the query time is 6 times or 5 times faster, and the CPU time is also 5 times difference, right? So having the partitioning improved the CPU time and the query time by 5 times. It really depends on the scenario, like I said. It also depends on how the other indexes are playing in the game, but as a rule of thumb, if you have a workload that has filters, that most of the workload is filtering on a specific string column, identifier of something, you do want to have a partitioning on that column, and that can give you a very significant boost. One thing, the interesting thing to see, and I'm just quickly going to show you, is how it looks in the statistics. And here, And there is another tab, it's called Query Completion Information. If you click on the execution time, it just gives you more information about what happened. So in here you can see that the scanned extents, when it was not partitioned, it had 145 extents, and it scans 140 of them. And from the 4 billion record, it scans 4 billion records, right? When I partitioned it, and the number of extents grew because now we have more partitions, right? And because we have more partitions, we have more extents. And but from the 467 extents, I only scanned 9 of them, right? And as a result, you can see that instead of from the 4 billion record, I only scanned 143 million, right? So that's why I'm getting such a performance boost. And the fun part about it is that I didn't need to do anything about my query. I don't need to think about it. Once somebody set this policy up, everything just works as you would expect. Okay, let's continue. Feel free to interrupt me with any questions, and happy to answer as I'm discussing the different features. Okay, so
no questions. I think that people is hooked into what you are presenting.
Okay, cool.
Thank you.
Sounds good. Okay, the next feature is weak versus strong query consistency. So what are these? So by default, Azure Data Explorer Kusto is running in a strong consistency. Strong consistency means that all the queries that are coming are going into the admin node. There is always one node in the cluster that is the admin, and it has the source of truth for the latest metadata. So it knows, it has the key to the metadata, and it has the latest metadata. And when the query comes into it, it can find all the latest data that arrived to the cluster. And obviously the query will be distributed, but the admin node is taking care of the query plan and ensuring that the query sees the latest data. So in a strong consistency mode, the data is always fresh, and everything gets the latest snapshot, and the admin node is taking care of all the queries. We have another mode that is called weak consistency. And in weak consistency, all the nodes of the cluster essentially can participate in this query handling, in this query management. That means that when you indicate on your query that you want it to be handled in a weak consistency, the gateway of Azure Data Explorer will send it to any node that it wants to. Usually it allocates, instead of 1 admin, it will use 4, but it's up to the internal logic to decide that. It will send it to a different node, and that node might not have the latest metadata. It might be lagging in 20 seconds, 30 seconds, something like that. But it will reduce the load on the admin, because now all the queries will be distributed across the different nodes of the cluster, and that will allow you to scale essentially the cluster and have the workload split evenly across the nodes. I have to say that we see quite a few cases where people are using just the default in a very high demanding workloads. They're using the defaults, and then they try to scale the cluster. The cluster is not behaving the way that they want. It's because the admin node is super, super busy. And what they do, they just add more nodes to the cluster, and that doesn't help at all because the admin still continues to be busy. And then we tell them, hey, use the weak consistency mode. And so far, it really worked well for most of our customers, but obviously we don't do that by default because we don't want to surprise anyone. But once we tell them or advise them to do that, immediately the load on the admin reduces, and then the whole cluster can scale, and then the customer can scale it to as much as they want to get the performance that they need. Okay, super important feature. You actually use it by telling each query comes with a flag that tells it whether it's a strong consistency or weak consistency. So you actually can decide that if you want some of the queries to be strong and some of the queries to be weak, you can do that. It's not a setting on the cluster, it's a setting on the query side. Okay, and now to the last feature, which is the query results cache. Query results cache is a feature that is similar to Redis. You know, a few years ago, we saw a few of our customers using Redis as the way to cache the results of the queries, and they had to manage both the Redis and the ADX database. And obviously, that was a lot of work. And we said to ourselves, maybe we can do it better. Maybe we can also provide server-side caching that will allow them to just, with a simple flag, just tell ADX, hey, we want you to cache the data, and we will cache it. And we did it actually in a very, I really like the design. You tell it by the query, so you can decide based on the query if you want it to use this cache or not. And you also give the expiration time for that. So you essentially say for each query, you say, I want this query to be cached for this time. Once this time elapses, then the query will run again, right? It will just ignore the cache will be invalidated. It's all managed by the Kusto cluster and super simple to use, like I said. What is the logic behind it? First of all, the cache itself is based on the identical strings. So if you even type one more space in your query, that will be considered to be a different query, and as a result, it will not look for the cache for it. So the key is actually the query string, right? It has to be going to the same database, and it has to have the same client request properties. Whatever they are, but for example, weak consistency, which we will just talk about. If one will come with strong and one will come with weak, it will not go to the same cache. So this is pretty much it. It's a super simple feature. So let's just look at it. We have another demo for this. Okay. So what we see here, I'm going to increase the font. Okay. Again, I'm going to show you a demo on our production cluster. So hopefully everything is well with it. It's a cluster of 500 nodes. It ingests a lot of data. And what I want to do is I want to do some chart of some clusters. So let's start first by looking what's going on this cluster. So I'm just checking to see how many records arrived to the cluster over the last, for 1 hour, starting from the go to hours. I'm just picking up some random time frame. And you can see that we got here 51 billion records, okay, in this 1 hour. Okay, and then the calculation that I want to run is I want to chart some behavior of the cluster. In this case, I'm going to look at the 10 biggest clusters that send us the most telemetry, the top 10. And then I want to look at the behavior over this hour by 1 minute bins and chart it. Okay, so I'm going to run this query. And this is a heavy query. I specifically chose a query that takes some time to complete because this is how you can see better the cache. So it took it around 9 seconds, and I got a result. It's 10 different clusters. I hashed them so you don't see any names or something like that, and you can see how they behave over time. Super simple stuff. Okay, so now let's, I'm removing the visualization so that you can see the result. And now let's set a query results cache for that for 15 seconds. Okay. I'm going to run this. This is the first time that it's going to run, so it's going to take another 6 seconds. And then I have the same query here with the same cache running here. You can see that this query, that query started, but it came immediately as with the other query. Why? First of all, because we had the cache, right? We set up the cache for 15 seconds. And then the cluster was smart enough that even if it was executing the query and another same exactly query arrived. It knew how to queue that, essentially put it in a special queue, and when the first query finished, it returned both of them to the clients. So this is it's just a very nice thing to do. Okay, but let's see how it works. First of all, I do that 15 seconds, assuming that the 15 second elapsed. So now it runs it again because the cache is invalidated. Okay, we'll wait for that to come back. Came back, now I'll run it again. And it tells me that it was run 4 seconds ago and return me the query from the cache. It's all immediate, right? If I run it again, it still got it. It was 12 seconds ago. 1, 2, 3. Now it's invalidated. And now the query will run again and we'll get the fresh data. Okay, so this is how this feature works. And with this, we are done pretty much with the features and what makes ADX, we feel, the best platform to build such an application. Now let's talk a bit about the UX stack and how people build those solutions. So ADX and Kusto has connectors to 3 main visualization platforms. One is Grafana, and Grafana is actually the one that invested the most in building those features into the connector. So in Grafana, for example, you can tell Grafana with just a simple setting, just by clicking a checkbox, you can tell it to calculate the size of the query results cache, the length or the time of the query results cache, based on the query itself on the dashboard. So if the dashboard, for example, is showing the last day, then the query result cache will be 10 minutes because you don't care about the last 10 minutes of the, you don't need to see the data refresh every second if you are looking at the whole day, right? What happens over the whole day within 10 minutes, nothing major, right? The last point might have changed. So in Grafana, the calculation of this caching window is automatically. Similarly, because this query results cache does identical strings, and the default in many dashboards is to show the exact timestamp. For example, if you choose that you want to see the last day, it will show you the exact timestamp of now versus the timestamp a day ago. In Grafana, they will change the query string to ensure that they will bin it essentially, to ensure that the query string matches, and you can really enjoy this query results cache the way that you intended to. So essentially the query results cache length plus the query results cache or the query string bins are well coordinated in the Grafana plugin to ensure that it always works and always gives you the best performance and the best utilization of the query results cache. So Grafana has obviously you can do all of that yourself in your own dashboards, in your own solution, but Grafana, it's all built in. ADX Dashboards is another dashboarding tool that we have. You can use all these features, like I said, weak consistency, query results cache, and things like that. You can use it from the ADX dashboard, but we don't have that as a global settings yet. Power BI is another tool that people are using for their showing users the different visualization. For the workload, Power BI has its own caching, so you can use the input mode. And what it will do is essentially will take the whole data set, the relevant data set, cache it on the Power BI side, and that will give the users a great performance. And then you can build your own UX and obviously use all these features and enjoy them. Okay, so that's the content that I made. I just talked about a few about next steps here, and what you are welcome to do is to read. We have a document that actually outlines this presentation. Please check it out. There is a couple of blogs that are very interesting about partitioning and the follower clusters that Yoni, who is the developer of this feature, created. And then I always like to reference my favorite blog ever created about Kusto. It's called Just Another Kusto Hacker. It's about internal competition that we did at Microsoft about hacking, writing some fun queries in Kusto. So for those of you who are interested in blowing your mind of what people can do with the platform, feel free to check it out and enjoy it. Okay, so I think we're ready for the Q&A, if there is any.
Thanks a lot, Avner. Very interesting presentation and demo, which is it's very relevant to what many of our customers and partners are looking for. And while we wait for more questions, there is one that is related to Data Explorer, not necessarily to the features we presented, but which I thought of elaborating here now because it deserves some explanation, which is how do you compare Azure Data Explorer with other market players like Elasticsearch and BigQuery in particular? How would you articulate what are the use cases in which Data Explorer performs best and it makes a good fit versus these two platforms?
Okay, thanks. This is a question that we like because it's so let me talk a bit about this. So first, I should say that historically, Kusto and Azure Data Explorer are the latecomers into the game of the big data analytics platform, and as a result, it has the advantage of looking at what the competitors have done and to obviously innovate and provide so even disruptive innovation around it. But we did compete, and we are competing with those two extensively and heavily. And I can say that about Elasticsearch, from the Elasticsearch philosophy is different than the ADX one. Elasticsearch is an indexing engine for text, and you can do analytics with it, which is what you get in Kibana, etc., and by searching for different strings and looking at facets. And you can also do a very sophisticated searches. You can do catalog search, you can do fuzzy searches, you can do semantical searches, and things like that. For telemetry, for machine telemetry, log telemetry, the one that we're using, the fact that Kusto created a relational engine that has the index, the text index embedded into it, gives a huge performance improvement over Elasticsearch. So this is what we usually see when we compare Azure Data Explorer Kusto to Elasticsearch. The first thing that we see is a much better performance. And it's very easy to understand why, because Elasticsearch is a text index, and Kusto is a relational engine that gives you analytics on top of it, but has the text index embedded. So obviously it's not the full text index. It's not, it doesn't provide you with fuzzy searches. It doesn't know how to, if you search for Mr. with MR dot, it will not find you the word Mr. M-I-S-T-E-R, right? It will just, it would not know that this is the same thing. And if you want to have this functionality, you go to Elasticsearch. This is where they excel. But in Kusto, when you search for the string Andrea or something like that, it will find you this string faster. I can say that it will find it even faster for you, but it will definitely allow you to do analytics on top of it, to count it, to aggregate by it, to calculate percentiles and things like that, much faster in a much cheaper cost. With BigQuery is the other direction. BigQuery is a relational engine that was built on a technology that Google developed called REML, and it's a very close to the philosophy or the design of Kusto in some ways. But BigQuery is, first of all, they did not go to the text analytics, I think, at least from what I've seen, they do not go to the text analytics in extent that Kusto does, with embedding very good text indexes into their data. Maybe they're already doing that, but as far as I can see, not. And the other thing is that the operators, the functions, the case insensitivity, things like that, that are built into Kusto by default and just started this way, in BigQuery you really have to work a lot to get the same semantics. You have to write regular expressions and things like that to get those text analytics done for you. And from what we've seen, but it's only, everybody should try it on their own. We've seen a better performance on Kusto. We feel that, we think at least that our engine is faster than BigQuery.
Thanks, Avner, for taking us through. And, yeah, no, and for your considerations. I mean, that definitely help our customers to make decisions and evaluate our services in the right light as well. And yeah, I do not see any more Q&A or questions. Sorry, and so, okay, before we close this session, maybe I'm going to take control of this slide from you, Avner, and maybe I just want to remind the participants of the next few sessions that we have in our calendar. And let me see. Yep. Oh,
okay.
I went a little bit too fast. Let's see if it works now. Yeah. Thank you. Thank you. So in the initial 3 sessions, we have done a little bit of quite an extensive overview of what services for what fully managed, I would say, services for batch-based and real-time analytics are available today on Azure, and we have had a deep dive in Azure Data Explorer, which is again one of the innovative technology that we have and a unique differentiator for us. For the next few sessions, so in the immediate next week, we will be talking about data governance, and we will provide an introduction to our Azure Purview. And then after Ignite, which is our main event in the month of November, we will get back with some sessions on machine learning, training machine learning models with a no-code or a low-code approach. And then we will move on to infrastructural services that are needed to be taken into consideration. For example, networking or repeatable patterns through landing zones, patterns or deployments. So these services are needed to bring your analytics system into production. And finally, we have added a deep dive specifically on security. And on the next slide, let us know as well what's your feedback from this session. We have a survey, and you can, yeah, here is the QR code to that. So your feedback is it's very important, and it will also help us shape these sessions moving forward, to tune them according to what your interests are. Let me see if there's some final questions. Okay, nice. The feedback is not a question. There's a feedback that this series and the session of today was great and very insightful. So thank you, Avner, for explaining and being with us today and explaining us at depth all the capabilities of Data Explorer. And thank you everyone for attending this session. See you next week.